This is Mrs. O'Neill for AP Chemistry, Chapter 9, Section 3, Molecular Shape and Molecular Polarity. Most of this stuff you already know. It's just a review, making sure you understand polarity and some exceptions to that polarity rule. So the objectives is to know the geometry of that molecule and, of course, to decide if it's polar or nonpolar according to the electronegativities of the elements bonded to the central atom. So again, I suggest pausing, fill in the blanks, play to hear my words. So a dipole, we want to remember, just means the same as a polar molecule. So a dipole has a partial positive and partial negative end to the compound. So we remember these from polar versus nonpolar shapes, and the geometry is going to help us decide if it's polar or nonpolar depending on its symmetry, correct? So remember, not symmetrical, polar, that means one element has more pull than the other, one element has more electronegativity than the other. Non-polar molecules are going to be very symmetrical, and the pull is going to be very, very equal amongst the elements on the central atom. So what do we mean by symmetrical, right? Again, the pull of those atoms according to their electronegativity. So here are the polar molecules, or the non-symmetrical. Bent, very polar, because again we have those non-bonding pairs of electrons. Trigonal pyramidal, again because we have the non-bonding pair of electrons, which you don't see here. Nonpolar, linear, the pull is very equal on both sides on that central atom. Trigonal planar, which looks very similar to what we just saw. I'm going to go back real quick. Trigonal pyramidal has the two non-bonding pairs of electrons, which I don't have here, but when you draw the actual molecule, you'll be able to see that. That's why drawing those Lewis structures is very, very important. And that's very similar, or looks very similar, to something that's trigonal planar. But here the difference is it's on a plane. Think about it as on one sheet of paper. It lies flat, so there's no non-bonding pair of electrons to make it a different pull. Those three blue atoms are pulling on that central atom very, very similar to each other, very, very equal. So it makes it nonpolar. Here's tetrahedral, again nonpolar because we have the four atoms pulling on that central atom very, very equally. So how can we make this nonpolar? This is a tetrahedral. We have carbon getting pulled by four chlorine atoms. Hopefully you remember from previous videos and discussions in class that all you got to do is change the elements. If you change the elements in any way, if they're different than the four that are going to be the same, if you change one, if you change two, if you change three, it now becomes polar because the pull on that electron, or the pull, the pull on that central atom is going to be different, making it polar. So there's the difference between a nonpolar tetrahedral and a polar tetrahedral. Again, what's the difference here? We just talked about this, right? There is the plane, so this is trigonal planar versus this is trigonal pyramidal because of that non-bonding pair of electrons. So they both kind of look the same. They both have three, or at least at this point, they have three electron domains, but when we draw the Lewis structure according to how you're supposed to draw it, you really, really need to add those two electrons here with nitrogen, that one lone pair of electrons, and this actually makes it 4 electron domains. So even though it looks like 3 electron domains, it's really 4 with those non-bonding pairs of electrons. So again, if you need to either review back on this video, review back on those handouts, review on page 344 and take a picture, however you need to understand what what molecules are polar versus nonpolar, the reasoning why, the structures, the Lewis diagrams of these compounds, you need to be able to do all of those things. Geometries, electron domains, polar, nonpolar, bond angles, and hybridization. So here's a chart that you can go through. I'm just going to go through this quickly. I strongly suggest filling in the shape, the polarity, and if there was any exceptions to the rule. Okay, so there's just a few examples, and again, this is to show you about the electronegativity these elements contain and why it would be polar versus nonpolar. So here we have an electronegativity of 3.44, which is different than the hydrogens of 2.2. The 3.44 on both sides of the carbon makes it very, very nonpolar. And here again, we have hydrogen has 2.2, oxygen is 3.44. So it's a polar molecule because the electronegativity is going to be different. Again, it just shows you how you make those positives to the negative or the pull of attraction. We went over these, we saw these. Hopefully this gives you a better understanding, again, of electron density and where the pull of attraction or the pull against the central atom is and why it would be polar versus nonpolar. Again, just showing you more of the quantum behind it, the quantum theory about the pull of attraction between those positives and negatives. And again, it's always based off of that central atom, right? So the central atom is going to, and how the elements around that central atom is pulling on it. Okay, see you in class.